Hello, I'm recording myself explaining example 5. So it is on page 50 of our reference book and figure 2.16. If you want to look at the ebook or book, so we have this circuit, we have our input voltage supply on the left side, and then we have this resistor, and then we come to this junction. I'm calling it node A, and then we have inductor L, and then the capacitor C, and the output is the voltage across this point. I'm going to call it VC. You would know that the VC is equal to VA if I'm calling the voltage on the point A, VA. So because they are in parallel, so this voltage across the capacitor is equal to the voltage across the inductor. Now, if I want to do nodal analysis or Kirchhoff First Law, so I'm looking at node A. So here I'm assuming that the current that is coming from this side is called I1, and then it is divided into two smaller current, I2 and I3. So I3 is flowing through the inductor and I2 is flowing through the capacitor. And then again, when we look at the point B, they add together and they make the current I1 back and goes back to the voltage supply. Now, let's write Kirchhoff's first law for the node A. So I1, whatever comes in, goes out. I1 is going to be equal to I2 plus I3. That is Kirchhoff First Law and nodal analysis. Now, let's write I1, I2, and I3. What do we know from them? If we look at the resistor itself outside the circuit, so what I can write is the voltage across this resistor is equal to the current that is the current that is flowing through it multiply in the resistance R. Now the voltage across this resistor will be the difference, the potential difference between this point here and this point here. And here we are looking at our input, the voltage supply, and here we are looking at VA or VC. Now we are looking at R. About R, we know that the V minus VA, which is the potential difference for our resistor, is equal to I1 R. That is the fact that we know about resistors. So from here, if I want to have I1 separate, I'm going to have V minus VA divided by R. And you know that we can replace the VA with VC. We can replace VA with VC. Just keep that in mind. So let's look at I2 and I3. So about I2, if we look at the current that is flowing through that capacitor, so about, I'm looking at C this time. So about C, that will give me the, let me look at, just double check with the book. Is it calling that I2 or I3? Yeah, that's it. So when we look at the capacitor, that is looking at I2. So I2 based on the table we discussed previously. So I2 is letter C, constant C, and derivative of, again, we can write voltage of node A or VC. So let's write it this way, and then we replace it with VC. Now let's look at the I3, the current that is flowing through the inductor. Now this time we are looking at the inductor itself. Now about the inductor, we know that I3 is equal to 1 divided by L, constant, multiplied in integration of, again, at this stage, the potential difference, again, sometimes we miss drawing it, but that is ground. So potential of that point is 0. So when we are looking at potential difference, will be at that voltage, subtraction of that voltage and this voltage. So then it will be minus 0, because one side is connected to the ground or going back to the voltage supply. So the potential difference of this inductor will be VA over time. And we know that VA can be replaced with VC. So let's substitute or replace I2, I1, and I3 into our nodal analysis. Kirchhoff law. I'm going to rewrite that after substituting I1, I2, and I3. Now for I1, I have V minus VA divided with R on the left side, and on the right side I have I2. My I2 is C derivative of VC over time plus the I3. I3 is 1 over L integration of VC dt. Let's tidy it up. So I want to have V on the left side and then VC on the right side. Remember I said we can replace that VA with VC? I'm going to do that. So I'm going to replace that with VC, and I also want to multiply both sides in R and then take that one on the right side. Then if I do that, on the left side I will have V, because I'm multiplying it with R. That R and this R will cancel each other and I will have only V. Now just I'm going to have R multiplied in both of those, so I will have RC dVC dt plus R over L, this guy is multiplied in R, integration of VC dt, and then that VA, which is replaced with VC, is going to the right side, so I'm going to have a plus VC here, and it has 1 over R here, which will be cancelled out when I multiply both sides in R. And that will be the relationship between our input and output VC. So on the left side, I have only my input, V. And on the right side, I have a derivative of my VC and integration of my VC and the VC itself. That's it. Okay, so I'm going to record myself doing the same thing, but different approach. I'm going to look at the mesh analysis. So Kirchhoff's second law. That's another way of getting to the same equation. Okay, thank you.